Hello,
Okay.
hello.
But what is happening? It's only me who is always kicked off, or everybody is?
No, Sasha, the problem is
Personally,
that I'm using the account of our department. And now someone else from the department, not enough disciplined, try to use the account at the
Or maybe
same
you
time.
did not tell anyone that you are trying to do this, so it's not so obvious that.
And I even know who it is, because the system doesn't notify me.
Okay.
And who it is?
I need
know,
permission
I
to share screen. It says host disabled participants
wait.
screen sharing.
Sure.
Okay.
Now you can.
No, you can continue.
Oh.
Thank you very much.
Thanks.
Anyway, I've just got some coffee. Okay.
No, it's a good idea to stop the seminar in random times so people get some coffee.
Yeah.
Why not? Okay.
Okay.
So how many breaks do you need? Yes.
Okay.
So so let's continue. So let me see. So we have talked about this switch thing, which is that we want to impose the constraints that first W has to be uniform, 0 or 1, and then it has to be independent of F, which is imposed by this. So the picture is like you can draw a 2 by 2 square, and then W will be on the horizontal axis, F will be on the vertical axis. And then you also have this V. This V satisfies this thing. I mean, this flip here. It says what? I mean, it says that first V is a function of W and F. V is a function of W and F. So and then it satisfies these constraints. So these constraints will mean what? I mean, these constraints means that V is only 1 in one of these 4 cells, right? I mean, and then it's 0 otherwise, right? So you can just, without loss of generality, like you can say that maybe it's this cell, right? I mean, because this flip will impose the constraint that V is only 1 in one of these 4 cells. So you can just, without loss of generality, say that it's this cell, right? If V is this cell, and then there's another random variable G, which satisfies this constraint. So this is like the wait, no, I mean, this satisfies this constraint. I mean, it's the same constraint, this flip Fg and V. So it means that this G, because this G is corresponding to different values of F, right? So it is like, so it must be here. So it must be on the corresponding to the value that F equals 0. So if V corresponds to F equals 1, then G must correspond to F equals 0 because of this constraint. So you have this thing. And then you also know that G is independent of W. So G must be something like this. So I mean, G will not be something, let's say, like this, because then that will make it dependent of W. Instead, it is independent of W, so it will look something like this. The picture looks like something like this. So you have V and G look like this. And we also have V bar. V bar will satisfy the same constraints as V. But then we also need, if V bar satisfies the same constraint as V, then since we know that V bar is like correspond to a different value of F corresponding to G, so V bar must also corresponding to F equals to 1, right? So it's on the same side as V. But then, I mean, it cannot correspond to the same value of W, because if V and V bar correspond to the same value of W, then this constraint will rule out that possibility, because this constraint says that V and V bar is conditionally independent given W. So if they are corresponding to different value of W, then if you condition on any value of W, then one of them must be degenerate, right? So this constraint is always satisfied. But if both V and V bar is equal to 1 in, say, this cell, then this is not satisfied, right? They are like conditionally dependent given W equals to 0. So this whole thing, I mean, this whole complicated thing would just it's just here to force this kind of joint distribution between this F and V bar. Is that like V? The more important thing is the W here, which is like W can have 2 values, 0 and 1. And then 0 would correspond to the case where Vi can be 0 or 1 with probability 1/2. And W equal to 1 would correspond to the case where V bar can be 0 or 1 with probability 1/2. So now you can like sort of like refer to the value of W, right? Because the case for W equals 0 and the case for W equals 1 is different in the sense that like one will make like V degenerate, one will make V bar degenerate. And then since we can talk about V and V bar, so we can kind of talk about the value of W now. Yeah, and then like this sequence, we have a sequence of W and V bar, so that we have like, each of these can represent one bit of information, but maybe there are many colors, so we will need a lot of bits to represent those colors. So this W is like a sequence of bits that will represent the colors. And then, yeah. So now we have like, we can think of this W as a sequence of these switches. There are altogether there are 2 to the power k choices because each of them has 0 or 1. So and then there are like maybe too many choices. It's kind of hard to like do math on that. So we want to reduce the number of choices of WK by requiring that there exists J, which is 1 up to k minus 1, such that either W is 1 if and only if I equal to J, or Wi is equal to 1 if and only if I is not equal to J. So it's like, this is like a one-hot encoding, right? This is like, we only allow sequence of W such that exactly one of them is 1, exactly one bit is 1, and then it's not the last bit. So the last bit is reserved. So it is either exactly one bit is 1 and it is not the last bit, or exactly one bit is 0 and it's not the last bit. So there are 2 times k minus 1 different choices of this WK. So we will use this as the colors. And the reason why we have these 2 cases, maybe we can just use this, right? Instead of considering both the case where it is exactly 1, 1 or exactly 1, 0. The reason why we consider this is that we will need like this W to be uniform between 0 and 1, right? So if we only have this, then it will be very imbalanced. There will be way more 0 than 1. So we can't make W uniform. But then if we have both of this situation, then we can like maybe use this half of the time and this half of the time, and then we can balance W. Each W will have like probably 1/2 of being 0 or 1. So now we have seen how we can define colors. The color is just represented by this sequence. And then we will just let Tk to be this set of colors that's allowed. So first, we will need to enforce that the color, the W can only take these values, right? The vector W can only take these values. It cannot be say 1, 1, 0, 0, right? So how do we do it? Is that like we have these constraints, which is we restrict that the entropy. For each W not in the set of permissible sequence, then this F is a function of this V and V bar and F. Maybe we'll use some example. First, like we'll look at what does F let's say what does this mean? If we have F. F is a function of V1 and say W1. In this case, what does it mean is that, let me recall that like F, the picture is something like this, right? The picture is that you have F equals to 0 and F equals to 1 and W equals to 0, W equals to 1. And then V1 is this thing, right? V1 is equal to 1 only here, right? So it means that if you have these constraints, then it means that if you are given W and if you are given V1, W1 and V1, then you can determine the value of F. This will only happen if W is equal to 0, right? If W equals to 0, then you can just the value of F is just equal to F value of V, right? So this is how, so this will enforce that W1 equals to 0. But then, if we have a sequence, W1, W2, and then we have like V1, V2, both V1, V2, and W1, W2. If the entropy of F given like V1, V2, W1, W2 is 0, then what does it mean? It means that I mean, because now, if at least one of this W1 or W2 is 0, then you can determine F, right? Because if W1 is 0, then you can determine F by V1. If W2 is 0, then you can determine F by V2. So if this thing, I mean, if any one of these hold, then you can determine the value of F, right? So you have the W1 equals 0 or W1 equals 1, right? So yeah, so this constraint is the same as saying that W equals 0, or W2 equals 0, right? At least one of them is 0, right? And then like V bar, I mean, the effect of V bar is similar, but the only difference is that like if you use V bar, then you are talking about like whether it's 1, I mean the value 1 instead of the value 0, right? So you can write this way. I mean, maybe use P instead of V bar here. So this thing, or you can also think of it. I mean, you can also talk about its negation. I mean, this is what? It is not W1 W2 equals to 1 1, right? So these constraints will mean that W1 W2 cannot be 1 1. So you will rule out the possibility of 1 1. So if you have a bunch of these constraints, then you can rule out any subset of W, right? Because I mean, if you have here, I mean, let's say you have V1 V bar 2, then this thing will be 1. I mean, here we're talking about 1 instead. Then you have this thing. I mean, you rule out the possibility of 1 0 here. And then like you can basically combine like this kind of constraints to rule out any subset of sequence W. So you in particular you rule out any sequence W that is not in this set of permissible sequence. So now you can enforce that W can only take value in this set of vectors. It cannot take value in anything else. Yeah, so up to now, then things are kind of like simple in the sense that like, I mean, here it looks like you can basically enforce any constraints, right? I mean, any constraint of W. I mean, you can enforce W to be in any set that you want. So I mean, it looks like we have already solved our problem, but actually not, because like this constraint can only act on one particular sequence W. But what if we have like say 2 different colors? I mean, like this constraint will enforce that like the set of color can only be say red, green, and blue, right? Because like this can like enforce constraint on any single color. So any single color must be in the set of permissible color. We cannot enforce something like say any 4 colors in the tile must be in a permissible set, right? Because this is only acting on one particular sequence W. So and in that case, then it turns out that like the kind of constraint we can impose on say set of 2 or set of 4 colors is much more limited. So that the 2 available is much more limited. But we will see how we can do that.
No, we don't need 4. If we say something about neighbor colors, it's enough.
Really? I mean, I'm not aware of this. so
okay,
is it
you just have finitely many tiles. So the neighbor tiles should be consistent. So if each tile is a kind of a color, then just the neighbor colors should be consistent. Why you need 4? Or maybe I don't get. No, I have to confess that I cannot follow anything in this complicated argument. So maybe somebody who understands it better can say something.
I think I understand why you disagree. I think the speaker means that a color is just a color of a side of a Wang tile. And in your question suggest to use the word color just as a name of
yeah.
which
You can consider tiles as colors, yeah. That's what I meant.
I think it must be possible. Yes, indeed. If we have some names for tiles, then the constraints touch only pairs of neighboring squares.
No, it's just the standard thing. If you have it, you can define tiling with 4 colors. You can say that each tile has, each vertex each node has 1 color, and just the pairs of colors on neighbor nodes should be consistent, allowed in some sense. So this is kind of.
But anyway, it seems that if we're able to go through all this encoding and impose the constraints for pairs, then probably we can do it for any finite set. Maybe it will be just technically more difficult.
Wait a bit. It seems that Sasha and Andrei, you understand it much better than me.
No. It's impossible.
No. It was an illusion. We do not. Don't worry.
Wait. Maybe still you can explain to me. So somehow we need to model by random variables tiles. So can you explain me, do we represent each tile by a random variable or what?
Yeah.
No.
Actually, the construction I use is that I actually represents the edge using each node of the torus. So it is like we assign color to each edge. So it's like each edge has a color to it, and then each tile has 4 edges. So it is like we need to enforce that. Like so basically the way or maybe we can do the next slide.
But the number of tiles is a priori not bounded by any a priori constant, right? But the number of variables in our constraint is bounded. So how can it be that we have one-to-one correspondence between?
So the thing is that like this torus constraint does not have any constraints on the size of the torus, so it can be anything. So this constraint only say that it forms a collection of torus, but there's no bound on how large this torus can be.
So I think that
we only have bound on say how we want like how large the set of colors can be.
So if you have more tiles, you have a more complicated formula in this logic, I guess. If you have more colors, you have so the formula depends on the number of colors.
Yeah? Yes, you are right.
No, Sasha, I mean, assume that we have fixed the tile set, right?
Yes.
But now my question is not about the tile set, but about the periodic tiling. The period might be arbitrarily large. Right?
Period may be large because the torus is represented as a pair of product of 2 circles, and circles is represented as edges in a graph which has cycles. So this torus and this graph is a cycle, is a pair of random variables which have very strange property which guarantees that the pairs of possible values form a cycle.
Okay, so how we represent the colors of edges?
Yes, so so this will be covered like later. So we will go into like how to encode like the color of edges later. But I think it's probably correct that maybe if we can impose this constraint on any pair, it will be enough. But I guess like in this proof, then I will actually impose this constraint on any 4 of them, like every set of 4 edges in each tile, because I'm kind of more like maybe it's an oversight of my part that I'm more focused on the original formulation of this tiling problem that we need.
Since your construction is rather technical.
You are right. Maybe the easier formulation is that we will consider tiles. Like,
you can benefit from simplification the tiling side. Tiling side is more or less standard. So if you simplify something there, you can maybe get a simpler construction a bit. But okay.
Yeah, you are probably right, but my proof will be based on like set of 4 colors.
Okay.
But I think it's probably possible to simplify the proof.
But I think you should be aware that none of, I don't know, maybe now people who commented confess they do not understand the details. So maybe you can just show somehow the kind what is happening in the proof without detailed explanations, and then explain, or maybe somebody who understands this can explain the intuition again.
Yeah, so maybe we'll skip to the end and then go back here.
No, just show some slides. We can get idea how it looks like.
So the picture is always, I mean, I guess it's hard to skip to the end, but yeah, we will eventually get to that. So it is like, maybe for now, then we would, the picture will only be that, like, we have a torus, and then we have a color on each node of the torus. I mean, each node will have a sequence WK. WK has a function of this node, x1, x2, y1, y2. And then we want to impose constraints on, like, say, neighboring pairs, and maybe like a set of 4 colors on each square. And then later at the end, we will see how this can correspond to the periodic tiling problem. Yeah, so sorry about that. Maybe like for the exact correspondence between this problem and the periodic tiling problem, then maybe we'll need to wait until the end of this talk. But for now, then the question is merely, I mean, we want to color the nodes in this torus so that every, like, say the 2 colors of every edge must satisfy some constraints. So this is the current, like, the problem that we are trying to solve. Yeah, so like, I mean, now the problem is that, like, yeah, so we want to assign color to each node of this torus. So this is, like, imposed by these constraints here. I mean, this W is a function of x and y, and then the rest, these things are conditional independence of like the node given the color. So now, I mean, how do we make sense of edges here? Is that if we condition on x1, x2, y1, I mean, but we don't condition on y2, then there are 2 possible choices of vertices, right? So for example, we constraints on, say, x1, x2, y2 is equal to, y2 is equal to, say, 1, y2 maybe 2, then it means that it is either this one of these 2 nodes, right? So if we condition on x1, x2, y2 is equal to 1, 1, 2, then the distribution of node is uniform between these 2 nodes, right? And then like if we, in general, if we want to condition on x1, x2, y2, then we get all of these edges, right? These edges, right? These edges, all these edges. I mean, yeah, so and so forth. And then we can also condition on x1, x2, y2. If x1, x2, y2, then you get, like, wait, no, I mean, no, I mean, these edges, right? And then also these edges, right? I mean, if we instead conditional on x1, x2, y1, then you get these edges, right? These edges. So I mean, if we consider both of these situations, then we get, like, all the vertical edges, right? And then you can also consider condition on x1, y1, y2, and x2, y1, y2. Then you get all the horizontal edges. So now you can make sense of edges. And then now we will see how we can impose constraints on each of these edges. So the way we do it is that, like, we will let E to be x1, x2, y1. Conditional on any particular value of E, then there are 2 colors, right? I mean, there are 2 nodes, and each of these nodes have 2 colors. So it means that the distribution of WK will be uniform between, like, 2 vectors, right? And then, like we want to enforce that some constraints on this edge. So first we will, I mean, for the introduce this notation that is this sets of WK and S bar. It is the product, like, this will mean that for each index in the set S, then Wi, the index has I in S, then Wi needs to be 1. And for each index I in S bar, then Wi needs to be 0. So it is this number that is 0 or 1 in the case whether like all those indices in I are 1 and all these indices in S bar is 0. And then one thing is that if we consider the conditional entropy of F given this Vs and V bar, S bar, and Wk, then it is the expectation of like this set here. So how do we enforce that for each edge, the number of color with that satisfy this set? I mean, for any of this set S and S bar is 1. And then like the number, we want to enforce that for each edge, the number of colors that satisfy this cannot be exactly 1. So it is either one of these satisfy this constraint and one of the other set does not satisfy this. So it is like in this case, then we will enforce it by these constraints. So we will see in the next slide why does this make sense. And then another possible thing that we can do is that we enforce for each edge, the number of colors W that satisfy this is at most 1. So there's at most 1 edge that satisfy this. So also one thing is that this kind of constraint is pretty much the only kind of constraint that you can impose on edge, because for example you cannot say that the first node will satisfy this constraint and the second node will satisfy another constraint, right? Because you cannot identify which node is which node. I mean they are like more or less interchangeable. So you can only ask like whether this set of colors satisfy like this constraint, whether all colors satisfy the constraint or how many of these colors satisfy this constraint. So now, I mean, we'll see in the next slide why this will make sense. Is that, so the first constraint is that like there exists U such that U is uniform among two values. And then like U is independence on the node, and this Vs and V bar S bar, and also F is a function of this. So in this case, I mean so this is this case here. So this will rule out the possibility that, I mean we want this constraint to check whether the number of colors satisfying this constraint is it cannot be exactly 1. So we want to rule out this possibility here. And then the reason is that like if like you have for this case, then you can obviously construct such U, because like you need the U, I mean, to be such that F is a function of this bunch of things and U, right? So here, I mean, F is already a function of V, so you don't really need additional information. So you can just take U to be anything, and then F will still be a function of this thing. And then for this case, when none of these are satisfied, it means that V is degenerate. If V is degenerate, then you can obviously construct U, which is just equal to F, right? If you just construct U equal to F, it will satisfy this constraint. That is, U has to be independent of V. And also F is a function of like V, U, and V, right? But the only case that is impossible will be this case, because in this case, then you cannot possibly have something that is independent of V and still you cannot have U that is independent of V and F is a function of U and V, right? F is a function of U and V. And then U is independent of V, right? So in this case, it's impossible. Because like if you want U is independent of V, so you consider the case where V equals to 0, then you have 3 possible choices here. But then U is uniform 0 or 1. And then you also need F to be a function, right? So you need to distinguish these two cases. But then now this probability of this is like 1/3, so it's not 1/2, so it's not possible, right? So this is impossible. So you can see that this constraint, like indeed will enforce that, like it is not this case in the middle. And then similarly, you can also do it. I mean, if you change the 2 into 3, then you can rule out this possibility, but you can keep this possibility. So you can impose this kind of constraints here. And then like similarly, you can also impose this kind of constraints for every like face of for every square. I mean, now instead of like having edge where like the color is uniform in the set of size 2, now you have color that's uniform in a set of size 4, then you can still impose this kind of constraints. And now we will talk about how like what to do about the phases. Is that like you condition on x1, y1, then there are 4 possible vertices. I mean, for example, here you have what? I mean, x1, y1 equals to 1, 1. In this case, then there will be 4 possible vertices, and it will form a square, right? So we will call it a type 1, 1 face. Type 1, 1 face is this kind of face. I mean, it is like it's this one, or 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 this one, right? And then similarly, if you condition on x2, y2, then you can get type 2, 2 face. And then we will ignore the type 1, 2 and type 2, 1. So what we will do is that we will enforce each type 1, 1 or type 2, 2 face has a set of colors that is in the set of allowed tiles. So yeah, so the picture is like this, right? So first, I mean, the type 1, 1 face are these squares that are gray. And then the type 2, 2 face are the head squares. And then now you will color each node such that, say the set of for each type 1, 1 face, the 4 colors must be in the set of permissible colors, like on the bottom. So this, you can impose this kind of constraint using the idea that we discussed. And then you can also impose this kind of constraint for each type 2, 2 face. But then we do not do anything for other phases like type 1, 2 and type 2, 1 phase. And then now, if you look at this picture, and then if you tilt your head like 45 degrees, then you can kind of see that it is the same as the periodic tiling problem, right? Because now, I mean, for each of this phase, you can kind of consider like a tile like this, right? You can get this like a square rotated 45 degrees. And for each type 1, 1 or type 2, 2 phase, you can pretend that it is a square this way, right? And then so and so forth, right? So now you have a tile. You have a bunch of tiles, but these tiles are rotated like 45 degrees compared to the torus. So now you have something like this.
So nodes of the grid, they really correspond to edges of tiles?
Yes, right. So nodes in the torus correspond to edge of the tiles. So now, I mean, each edge will have a color. And then the sets of 4 edges in each of this face would need to fall into one of these allowed sets. So now you can impose that each of these tiles, I mean, this like rotated 45 degrees squares, need to be one of these squares here. And then this will also like the constraint that like neighboring tiles, like the touching edges of neighboring tile has share the same color is automatically satisfied because they correspond to the same node. So yeah. So now we have seen that like how we can like find embed like a problem of periodic tiling using this like coloring of torus. Yeah, so this basically complete the proof. I mean, there's still one step is that like because like we need each of these wi to be uniform between 0 and 1. Then it means that like for each so let's say for a case where k like there are like the sequence W has length 4, then you have like 6 possible colors. I mean 1 0 0 0 0 1 0 0 0 0 0 1 no 0 0 1 0. I mean we reserve the last bit, so and then it is like 0 1, 1, 1, 1, 0, 1, 1, and 1, 1, 0, 1. And then because we impose that each of these WI must be uniform 0 and 1, so we need the number of nodes with this color is the same as number of nodes in this color, and number of nodes in this color is the same as number of nodes in this color, and so on and so forth, right? Then we can impose the constraints that then we can know that WI must be uniform. And in this case, because now because we are allowed to have more than one torus, right? So what we will do is that in order to satisfy this, we will just take one tiling. I mean, we will construct one torus and then copy it and then flip all the color, right? I mean, let's say we construct a tiling on this torus, and then we will just copy this torus, and then we will flip a color. I mean, if it is this color, and then we flip it to this color, if it's this color, we will flip it to this color, and so on and so forth. So we will have a flip another torus that consists of flipped colors, and because like these constraints, the torus constraints, the tori constraint only enforce that it's a collection of torus, right? So you are free to have lots of torus. So you can make this W balance this way. So yeah, so this is basically the proof of this theorem. So we have seen that we can convert a problem of periodic tiling to a problem of coloring this torus, which can be expressed as this AEIP. And since this periodic tiling is undecidable, then AEIP is also undecidable. And then we have also seen that we have only used constraints on in the form of I mean, all the constraints we have used are basically independence or conditional independence, or the constraint that some random variable is a function of another random variable. And then this you can kind of express this as mutual information between x and x given y is 0. So this is basically, I mean, the constraint that we have used are all in the form of conditional independence and cardinality. So it also means that the conditional independence implication problem, if we impose cardinality, if we allow imposing cardinality constraints, then it is also undecidable. But then there are a few more steps that's needed. I mean, if we want to prove the conditional independence implication with cardinality is undecidable. So the first thing is that I mean, we have used uniform 2 and uniform 3 and uniform 4. I mean, we have used the constraint that the random variable is uniform with a support size 4. And also 105 is used in enforcing each face has a set of 4 colors which fall in in some sets. But then, I mean, obviously 4 can be, I mean, you don't really need 4 because something is uniform with cardinality 4 just means that you can break it into 2 parts, which each of these has uniform 2. And then it turns out that once you have 2, you can express any of these uniform cardinality constraints. But then, I mean, the proof is somewhat technical, so we will skip that now. But actually, just having 2 will be enough. I mean, it's enough to just have one random variable that is binary. And then you can impose any kind of cardinality constraint using this. And then another technical thing that we need is that here we are sometimes using this kind of constraint where maybe say x is a function of y. But then, I mean, some author, I mean, when they consider conditional independence implication problem, they require that A is disjoint of B. So they do not consider this to be a conditional independence constraints because it is more of a functional dependence constraint rather than conditional independence constraints. But then, I mean, you can actually convert. I mean, we have shown that we can actually convert this kind of functional dependency constraints into conditional independence constraints. So this is not a problem. So you can given any problem where A might be not disjoint of B, you can find an equivalent problem where all these A, B are disjoints. And then this will use the double Markov property. But yeah, that is also a little technical, so we will skip it now. Yeah. So maybe like at the end we'll give some like still problem that is still unsolved. So first is that like is the conditional linear information inequality decidable? So we have not solved this yet. So we really require affine inequality, right? Because like we require affine inequality to impose the cardinality constraints. So without like affine inequalities, then we cannot impose cardinality constraints, right? I mean, because like if a constraint, if a set of constraints is all linear, there's no affine inequality inside. Then if like you have like x1, like say x y z, I mean, if it is on 3 random variables, if x y z follow that constraint, then you can take 2 independent copies of it. You can consider x1, x2, and y1, y2, z1, z2. It will also follow that constraints, right? So you cannot really bound the cardinality of anything if you are only allowed to talk about linear information inequality instead of affine ones. And another thing is that like it's conditional affine information inequality for a fixed number of random variables decidable. So I mean, let's say n equals to 4, is it decidable? So because like our construction use so many random variables, so it's not clear whether if we have a fixed size, then whether it is still decidable, it is still undecidable. And then like also like what if we consider the almost entropic region? I mean, if we want to decide whether an affine subspace intersect an almost entropic region instead of just the entropic region, like if we consider the closure, if we consider almost entropic region, then whether this problem is still undecidable. So yeah, so this is still unknown. So yeah, so this is the end of this talk, and thank you very much. Thank you very much. So if you have any question, then please feel free to raise it now.
Yes, thank you.
So
yeah.
Thank you very much.
Thanks a lot.
Yeah.
And it's very impressive. I should say that somehow a lot of things can be expressed in terms of this conditional inequalities. And so how can you say, what was the crucial thing? Just you invented all this technique of representing combinatorial things in terms of inequalities, or this technique was already somehow known, and what you did is just to find the connection between periodic tilings. So I think that you say that some lemmas about uniformity was known before, but not the torus thing, and not the coloring, and not anything else. Yeah.
Yeah. So I mean, for the proof, like for the undecidability of like conditional affine information inequality, the only result that we use, the only previous result we use is these results. Otherwise, everything is new as far as I know. I mean,
actually, excuse me, just Sasha, if I make a comment, with all respect to Zhang and Yang, this lemma is not a big deal. It's a simple observation. Actually, we know that. I think.
Yeah. You know.
It seems that all the technical tricks used in this proof is something new.
Yeah. So for example, this idea of a torus representation in a cycle of graph can one say that this is something new and crucial? So this is one most important invention here. Is this cycles or something else?
Yes. I think this is probably the most crucial step here. I mean, once this picture, like I mean, when I was thinking about like proving this undecidability, I mean, the first thing that the first problem that I considered like a reduction from is the problem of like the solving the Affine equation, like solving like polynomial equation, where like the variable must be integers, and that problem is undecidable. I think it's Hilbert's like 10th problem or something like. So this is like so I originally think about like proving a reduction from that problem. And then actually it it is kind of promising because like you can actually encode X using a uniform. I mean, if here then X is like uniform in a set of size K, then you can use this random variable to represent this integer K, right? And then you can do multiplication here. I mean, if X is independent of Y, then the cardinality of XY is the product between these two cardinality, right? So you can do product here. But the only problem is that you can't do sum. I mean, you can't really sum the cardinality of two things. So it's impossible to express sum. It's impossible to construct a random variable where the cardinality is the sum of two given random variables. If we are only allowed to use this kind of constraints, impose this kind of constraints. I don't know if it's possible or not, but I couldn't do it. So I'm just like scanning through the list of like undecidable problem to see like what kind of reduction can I prove, and then the next one I stumble upon is this the tiling problem. And then because like now I already know how to do this uniform, then it looks like, I mean, once we can construct this a torus, then it looks like this approach might work, right? I mean, and now we have the torus, and more importantly, we have ways to make sense of edges and also faces of this torus, because I mean, it's important that each of these value of X and value of Y are indexes by pairs of this X1, X2, and Y1, Y2. Because now, I mean, if you have pairs, then if you condition on only one of them and do not condition on the other, then it is uniform along two numbers. So if you have these two numbers, then you take these two products, then you get a square, right? So I mean, not only you get a torus, but you also have a way to make sense of squares and edges, like using only like these random variables. I mean, if you condition on different random variables, then you get different squares and different edges. So I guess that, this is probably the most important step of this proof.
Mm-hmm. Thanks.
No, actually, if you're saying that this is the most important step, this is good, because this is still the slide that I could follow. What I couldn't follow is the next part when you encode colors of separate nodes using these triples of variables. This part.
But so you say that you understand the proof of this statement about graphs of the cycle form, yeah?
I think so, yeah.
Even you think why you understand why it's true. Okay, that's you can explain it later in more details and slowly for dummies. Okay, and if we consider variables with infinitely many values, do we have some what is known about this? We have a different class, or still we have undecidable, the same inequalities. So imagine we have countably many values.
Yeah, so all of this will work regardless of whether it is finite or countable. So because I mean this constraint will impose. I mean, if this constraint is satisfied, then it must be. I mean, if you also know that they are all of this random variable are discrete countable, then it must be finite. So after you impose the constraint, then everything is finite. So it does not really matter whether we start with like countable or finite random variables. Mm-hmm. So at the end, we will still arrive at finite because of these constraints.
But what is known in general, the entropy region is the same or not? Or the closure of the entropy region is the same?
I think they are more or less the same.
I guess the closures must be the same, but I'm not sure about exactly entropic points. Perhaps with countable many values, we can simulate the limits of usual entropic vectors. Just I'm not sure. Just it seems it must be
but
possible.
Like I don't know. My impression is that like finite and countable is not really that different, but most people just consider finite just because that will guarantee that the entropy is finite.
But
Then
perhaps,
my impression is that like you don't gain that much by considering countable.
perhaps Laszlo knows the answer.
No, definitely I do not know, but things are not so simple at all. So this Zhang about the triples, it simply doesn't matter whether you have finite or countable support. Okay, so this is still true that there's a lot of missing things, so that you cannot get by the countable supports too many. Okay, the boundary still will be just very problematic. You say, so that definitely it is not so easy if you are just switching from one thing to the other. So that this is okay. So that this is still complicated. Thanks. So things might be there, but definitely there will be a lot of problems around here. Okay. So that's it.
Yeah, I see.
So it is
So
not,
this, yeah. So this, I think this will work for both finite and countable case, but it won't work for continuous, I think. I mean, for continuous random variable, then all of this won't work, I think.
But for continuous random variable, probably you need to consider only information. You cannot just have entropies.
Yeah, probably.
And
but you can still make sense of say this constraint, because that will means that y1 is almost surely a function of y2 and y3. So it's continuous, and you can still make sense of it.
This is possible, but just the inequalities for entropies may become meaningless unless you can rewrite them in some form of information.
No, this conditional entropies, they are completely fine with continuous variables. So conditional entropies, there is no problem, and very probably lots of things go through. So that what the main point here is that uniformity and the size of the support can be expressed as equations on these conditional entropies. Yep. So that, and after that, whether the support can be countable or not, so that it simply doesn't matter. It is those equations simply restrict the supports to be finite 2 or 3, and also they force the distribution to be uniform on its support. Okay. So that's the main. Very nice result. I'm just trying to digest it, and still maybe okay. And also I see that the periodic tiling, it comes from this torus-like structure. And okay, that's all. That's the main point. So that if you have a set of tiles, then you have to construct from the set of the tiles the appropriate problem, which also means that you have to encode all of the codings in a certain way. You need a huge big formula. So that this is still we have to understand exactly the complicated part, that who the coloring is supposed to just get, but okay. Anyway, the initial steps are just clear. So that was wonderful. Thank you very much.
No, this finite torus also used if you want to show that the set of formulas which have finite modals is undecidable. You also consider finite tori, and so this is not so unexpected. But what is for me, what is really unexpected is this strange cycle thing, which somehow embeds this structure into very. And also the philosophical question: if we are interested in kinds of law of information in a more philosophical sense, it's your example about this splitting of information random variable into a pair of independent random variables. It's what you showed, that was 1.6 and something like this.
Oh,
it's kind of very because it's something which probably is much different in algorithmic information theory, when you can take a shortest program, split into two programs, and both are random with respect to uniform distribution, so more independent and so somehow there is some effect with this impossibility of splitting, which has at least no visible parallel in algorithmic information theory, or I am missing something here.
So what will be the corresponding problem in?
No, just if you have a string, then you can find information equivalent pair of string xy, which are independent and random with respect to or just independent and have half of entropy.
Oh, really? So
no, because if we are interested with logarithmic precision, actually every string can be compressed into a random one, and then we just take two halves of this random string, and they are independent because you have maximal complexity.
Yeah, but what if like the string are not uniformly distributed? Like,
no. In algorithmic information theory, there is no distribution. We just take a minimal program for it, and with logarithmic precision, it will be random, according to uniform distribution. Otherwise, it could be encoded even more in a shorter way. But
I mean, if you want to find a program to like compress like half of the string, then does it necessarily mean that the length of the program is half, or do you still need the same program?
No. You of course you should split not the string itself, but the shortest program. But let me ask a more specific question. Imagine that in this U prime, in this statement about splitting X into parts.
Yes.
Imagine that you allow some not exactly zeros, but more or less they are approximately independent with up to some very small relative error.
Precision.
Yeah. Then it's again, there is a kind of bound that you cannot achieve. You need 1.6 or you cannot come to close to 1. Or it's no more true.
So if we consider like the question of like that's like if the random variable of interest is actually a sequence x1 up to xn, this is also IID sequence. Then as n tends to infinity, then of course you can divide it evenly. I mean one obvious way to divide it is
just to split the sequence itself. It's not a problem.
Maybe a subsequence. I mean, you just divide the sequence into L parts and then. But another way is that it's the reason why this works is that like now the information spectrum. I mean, if you consider log of 1 over probability, then this thing will by law of large number it will concentrate. So it's like most of the possible values of this sequence are concentrated. Like they are more or less uniformly distributed over this set of typical sequences. So because of if it's uniform distribution, then you can obviously do this. I mean, then you can just like if it is uniform or in a set of size 2 to the power L, then you can obviously divide into L parts. And then,
so what you say that for approximate things, it's not true anymore, the statement, and you more or less can split in a reasonable approximate sense.
Yes. So it really depends on how uniform X is. So if X is very uniform, it's actually very close to uniform, say if X is itself an ID sequence, then you can do it, I mean, with a very small penalty. But then, I mean, if in general, I mean, X can be very non-uniform, then in this case, then you will have penalty in this. So you can actually show that. I mean, this is in this paper, I kind of start with one question that is like the set exists are infinitely divisible. Like is information infinitely divisible? It means that like the set exists a random variable X so that this thing is always possible. So this thing, instead of 1.6, we have 1 here, then this is 0. So it means that like this will of course means that entropy of UL given X is also 0, right? So it is like the sequence UL will have the same information as X. So the question is that does there exist a random variable that you can break it into as many parts as you want, as many IID parts as you want, and they can this part all of this part must have the same information as the original X. So this question is I mean, as you would expect, it's actually impossible. So you can just like prove it by considering like the probability mass function and stuff. So I mean for the like so to relax this thing a little bit, then we consider maybe we will need to impose like a multiplicative penalty, and then it might be possible. But then, I mean, like, I think in general, if you do not impose any constraints on the distribution of X, then you would need a multiplicative penalty. I do not have a proof of it yet, but I believe this is true. I mean, wait, let me think.
Assuming that you require exact equalities in the left-hand side.
Yes.
Yeah.
But then, is there any way to relax this so that, yeah, I kind of doubt it, because like, unless you also have some constraint on the distribution of X, but otherwise then, because X can be like some very ugly shape, then it is. And it's not very clear how you can evenly divide it.
Sasha, I think
so for Kolmogorov, for Kolmogorov complexity, there is this result of mine about online Kolmogorov complexity, where for big L, we cannot split the program in many small parts.
Oh.
With what precision?
So if L is linear in the information, then we also have a weird constant for the best upper bound. You remember this? It's done 10 years ago, but
yeah, but
do you have additional log terms allowed or not?
No, the discrepancy is linear.
No, that's online thing. It's another story.
No, but you can, if you can break it up, you can combine it back. And since after combination we cannot, so imagine we could break it up, then we could combine it back, and the information and all the pieces must, the sum of them. Okay, so maybe I'm confused.
Can you share your paper with me, or can you maybe send it to me via email or on the chat?
Yeah.
Maybe I can take and read it in detail.
Yeah, but I'm a bit confused myself how it relates. Yeah, I will send it.
Yeah, thank you very much.
Okay, I think we need to finish because somebody else wants to use the account.
Oh.
Okay. Thank you.
Thank you very much.
Thank you very much.
Yeah, so if you have any more questions, then please let me know through email.
Thank you.
It's very interesting work. Yeah. Thank you.